Hi students, so in previous classes we have discussed about minimum and maximum modes of 8086 and now this is the last unit of our first unit. This is interrupts of 8086. So this interrupts concept that I am going to discuss with you, what is interrupt and what are the classification of interrupts and what is interrupt vector and interrupt vector table. So like this I am going to divide and I am going to explain you each and every part in detail now. Okay. So first let us see about brief introduction of this one, interrupts. So while CPU is executing a program, an interrupt break the normal sequence of execution of instructions, diverts its execution to some other program called as interrupt service routine. So interrupt is nothing but interrupt is a break or interrupt is a disturbance to the current program. So whenever a processor is executing a program, it disturbs that particular program and diverts the execution to some other program. That some other program is called as interrupt service routine. After execution of interrupt service routine, the control is transferred back to the main program. Once the interrupt of 8086 got executed and the control is transferred to the program. So whenever a number of devices interrupt a CPU at a time and if the processor is able to handle them properly, it is said to have multiple interrupt processing capability. That means whenever the processor is having more number of disturbances and then if the processor is capable to handle all of them at a time, then that processor is having a multiple interrupt processing capability. So we are having from pin diagram of 8086, we have already seen about NMI and INTR pins. 8086 has two interrupt pins, those are NMI and INTR. NMI stands for non-maskable interrupt. Any interrupt at NMI cannot be masked or disabled. So INTR interrupt may be masked using interrupt flag. So INTR is of 256 types. So INTR interrupt is of 256 types and this non-maskable interrupt that we can't disable it, okay, and but INTR interrupt can be disabled. INTR may be from 00 to FFH. If more than one type of INTR interrupt occurs at a time, then an external chip called programmable interrupt controller is required to handle them, okay, if more interrupts come at single time. So this is about introduction to interrupts, and now we are going to see the types of interrupts. So the interrupts are classified into hardware interrupt and software interrupt. So in hardware interrupt we are having maskable and non-maskable interrupts. So hardware are otherwise called as external in some cases. So hardware interrupts can be caused due to an external device or any signal or else any device that is associating with the processor, any peripheral with this that is associating with the processor. So for example, any keyboard interrupt. So internal or software interrupt generated internally by the processor circuit or by execution of an interrupt instruction. So this is software interrupt that occurs internally. So software interrupt is divide by 0, overflow of interrupts and interrupts due to int instructions. These are the examples of software instructions. So now we are going to see a brief about hardware instructions and what happens for NMI and INTR pins with the in association with the registers of 8086. So hardware interrupt is caused by any peripheral device by sending a signal through a specified pin to the microprocessor. So it is caused by a interperipheral device and it is sent to microprocessor by a specified pin. The 8086 has two hardware interrupt pins, they are NMI and INTR pins. So NMI is a non-maskable interrupt and INTR is a maskable interrupt. Non-maskable means that can't be disabled, okay. So INTR is having lowest priority by comparing the NMI pin. So one more interrupt pin associated is INTA. It is called as interrupt acknowledgement, okay. So now we are going to see about non-maskable interrupts. So in non-maskable interrupt, it is a single non-maskable interrupt pin having higher priority than the maskable interrupt request pin INTR, and it is of type 2 interrupt. Okay, we are going to see the types of interrupts also. So when this interrupt is activated, the following actions will take place. So completes the current instruction that is in progress. Whenever NMI comes into picture, the following steps will take place and pushes. First it completes the current instruction to be completed, and it pushes the flag register values onto the stack and pushes the code segment value and instruction pointer value of the return address onto the stack, and instruction pointer is loaded from the contents of word location. Code segment is loaded from the contents of next word location, and interrupt flag and trap flag are reset to 0. So instruction pointer, code segment, flag values and everything will affect by NMI pin like this. And next one is interrupt. INTR means interrupt request. So INTR is a maskable interrupt because the microprocessor will be interrupted only if interrupts are enabled using set interrupt flag instruction. It should not be enabled using clear interrupt flag instruction. So any interrupt can be enabled only by using setting the interrupt flag instruction. Okay, so whenever IF is equal to 1, then only interrupt comes into picture. So INTR interrupt request is activated by an IO port. These actions are taken by the microprocessor itself. So it first completes the current instruction. Okay, the following steps will come when INTR comes into picture, and then activates a interrupt acknowledgement output and receives a interrupt type. Let the interrupt type be X. So flag register value, code segment value of return address and instruction pointer value of return address are pushed to the stack, and instruction pointer is loaded from the contents of word location. Instruction pointer means that is the interrupt type into 4. So code segment is loaded from the content of next word location, and interrupt flag and trap flag is reset to 0. So these are all the steps that will happen whenever INTR, any interrupt request which is a maskable interrupt, comes into picture. Okay, so first both NMI and INTR they completes the current instruction and then activates our interrupt and then follows again step. So in INTR, whenever interrupt request is there, it executes the instruction and it receives the interrupt acknowledgement device, and then it changes flag values, code segment and instruction pointers as I have discussed earlier. So next is software instructions interrupts. So software, in some instructions are inserted at the desired position into the program to create interrupts. These interrupt instructions can be used to test working of various handlers. So it includes interrupt instruction with type number. So it is a 2-byte instruction. First byte provides the op code and the second byte provides the instruction type number. So there are 256 interrupt types under this group. So the software interrupts are 256 software interrupts. So its execution includes following steps: flag register value is pushed onto the stack, code segment of the return address and instruction pointer value of the return address are pushed onto the stack. So complete stack is involved with interrupts, as we have seen NMI and INTR also is happening. IP is loaded from the contents of the word type number into 4, and code segment is loaded from the contents of next word location, and interrupt flag and trap flag are reset to 0. So you can find some similarities between INTR and software interrupts here. So this is the interrupt cycle of 8086. So how an interrupt is getting executed in 8086. So when any external device interrupt the CPU at an INTR pin while executing a program, the CPU first completes the execution of current instructions and IP is incremented to the point of next instruction. So we know, right? So IP for each and every instruction pointer will get incremented by one location. So the contents of IP and CS are pushed to stack. The CPU then only acknowledges requesting device immediately on INTA if it is a non-maskable interrupt, trap or divide by 0. If only for these three interrupts, then only CPU gets acknowledged immediately to interrupt via interrupt acknowledge pin. If it is INTR request, the CPU checks the interrupt flag. So if interrupt flag is set, then it acknowledges the device, otherwise the interrupt is ignored. So if IF is equal to 1, then only interrupt acknowledgement will be sent if it is INTR request. When interrupt flag is 0, then the interrupt is ignored. After acknowledgement, the CPU computes the vector address from the type of interrupt, and then control is transferred to ISR for serving the interrupt device. So whenever it gives acknowledgement, so after the acknowledgement it computes the vector address of the interrupt vector table, and the control is transferred to interrupt service routine. So ISR, interrupt service routine address, is available in interrupt vector table. At the end of ISR, last instruction should be IRET. Okay, so whenever the program goes to interrupt service routine, so after execution of interrupt service routine, IRET is the instruction, that is interrupt return is the instruction that has to be the last instruction for any ISR program. That should be recognized by the processor that the interrupt or interrupt service routine is completed, and the program flow is turned to the main program. So you can see here, this is our main program. These are the steps, like that it is flowing, and here any interrupt is came. So whenever interrupt comes into picture, this is code segment is to instruction pointer. So these both are push to stack, push instruction pointer, push code segment, push flag register, and fetches the interrupt service routine address. So whenever interrupt service routine address is fetched, then they directly go to the ISR and execute the program that is there in the interrupt service routine. So they have to execute our interrupt service routine. So whenever interrupt service routine is executed, that means this program is executed in this way, and whenever the final instruction RETI or else IRET, okay, whenever the instructions interrupt service routine finds out this instruction IRET, which is the last statement of our any interrupt program, interrupt service routine program, then automatically after this instruction it pop IP, pop CS, pop flag. Ante that means from stack register it pops all the values, and the program execution flow will be returned to the main program. Okay, so like this, and the main program will be executed continuously. So whenever in any microprocessor, let me be a bit clear. So whenever a microprocessor is there, so microprocessor is executing a program, so it is a program. So whenever any interrupt comes to microprocessor, so this from this program it goes to another program called as interrupt service routine. So in interrupt service routine there are some programs, and the last instruction of interrupt service routine is IRET, that means interrupt return. So whenever interrupt return comes, then automatically the program flow again goes to your microprocessor program, and the program executes completely. Okay, so this is in this way an interrupt service routine works. Okay, this is the main flow of interrupt in 8086. This is the processing of interrupts, and you can see over there nested interrupts. So nested means interrupts in interrupts like that. So this is the main program. So in main program there exists an interrupt at 0AH, and from this interrupt it goes to ISR, interrupt service routine 0AH, and it is whenever interrupt service routine is getting executed, and if we found out any another interrupt, then it goes to that 0B address and it executes the interrupt service routine of 0BH address, and whenever it finds IRET instruction, the last instruction of ISR, then it goes back to the interrupt service routine of 0AH program, and it completely executes the 0A program. So whenever if you found IRET at 0A program, 0AH address program, then it returns to the main program. Like this the nested interrupts in 8086 works. Okay. So there are three sources of interrupts of 8086. So we have already seen hardware interrupts, software interrupts, and error in program executions. So hardware interrupts means that we are applying at NMI and INTR pins. Software instructions means in execution INT instructions, and error in program execution if it is divide with 0 error or else any overflow error like that. So 8086 uses 256 types of total software interrupts. So 250 types of interrupts are classified into dedicated interrupts. So the dedicated interrupts are type 00 to type 04, total 5 interrupts, and reserved interrupts are 5 to 31, total 27 interrupts, and available interrupts are from type 32 to type 255, total 254 interrupts. Okay. So the dedicated interrupts are type 0 is divide error, type 1 is trap mode single step execution, type 2 is non-maskable interrupt error, type 3 is breakpoint, and this is the most common used interrupt program in our ALP language that we are going to cover in our next unit. Type 4 is overflow. So these are the dedicated interrupts of 8086. And interrupt vector table. So whenever interrupt is enabled, the present instruction pointer and code segment are pushed onto the stack and loaded with the address of interrupt service routine, which is available in the interrupt vector table. So where this IP and CS gets this interrupt service routine address means in the interrupt vector table. So first let us know the difference between interrupt vector and interrupt vector table. So this is interrupt vector. You can see here interrupt vector. It is a memory block which contains the address of interrupt service routine, and the size of interrupt vector is 4 bytes just to store the CS and IP of instruction interrupt service routine. So the code segment is to IP address value just to store these value. The length of the interrupt vector is only 4 bytes. So what is interrupt vector table? It is a memory block which contains interrupt vectors. Group of interrupt vectors consists of together form as interrupt vector table. Okay. So since there are 250 types of interrupts, there are 256 interrupt vectors. Okay. So total interrupt vectors of 8086 are 256. So since the size of interrupt vector table is each interrupt vector is of 4 bytes, right? So 4 into 256, 1024 bytes. Okay. So now in 8086 interrupt system, we have seen the memory segmentation diagram. The first 1 kilobyte memory from 0000H to 003FF H is reserved for storing the starting addresses of interrupt service routines. This block of memory is called as interrupt vector table. So the perfect physical definition of interrupt vector table is this one. So in any 8086 system, 8086 is having total 1 MB of memory. So in that 1 MB of memory, the first 1 kilobyte of memory is used to store the starting address of interrupt service routine. So interrupt service routines, this block of memory is called as interrupt vector table. So interrupt service routines means we have seen type 0, type 1, type 2, like that we are have seen some dedicated interrupts, right? So to execute the type 0 interrupt, there exists a special program that is stored in the memory. Interrupt service routines occurs in these memory locations, and there are predefined programs which are used to execute the interrupts, okay, dedicated interrupts or else any interrupts that are coming into our program. The interrupt vector table contains 256 interrupt vectors. The interrupt vector table contains of address of ISR, and that is IP and CS values of ISR address, okay. So the interrupt vector address can be calculated by multiplying with type 4. That means for example, interrupt vector address for type 2 interrupt is 02 into H, that is 00008 H. So why we are multiplying with 4 means I have already told you the length is 4 bytes for any vector. So that's why we are multiplying with 4. So the final one of 8086 is the very important diagram, that is interrupt vector table of 8086, and you can see the memory locations from 00000H to 003FFFH, okay. So these memory locations, it is divided in, it is called as interrupt vector table. You can see first one is the dedicated interrupts, first 5. So type 0 divide by 0, type 1, each one length is 4 bytes, okay. You have to keep that in mind. See here 0, 4, 8, C, 10, 1, 0, like that it is coming, right? So each one length is 4 bytes. So type 0 divide by 0, type 1 is single step, type 2 is non-maskable, type 3 is breakpoint, type 4 is overflow, type 5 is reserved, and then from here type 5 to type 31 are reserved interrupts, and type 32 to type 255 are available or user interrupts, okay. That means any manual syntax errors or else any manual program errors, like that they will come under those programs. So each interrupt vector will be having, okay, each interrupt vector will be having a particular interrupt service routine program that is stored in the memory. So whenever the program execution, whenever the program hits an interrupt, it goes to ISR, executes that ISR and finds IRET instruction, and after IRET it comes to main program, and finally it executes the program. So this is the flow. This is the same flow for every dedicated interrupt, reserved interrupt or available interrupt. So this is the interrupt vector table, which is a very important one to for examinations as well as to gain knowledge also. So this is about interrupts and interrupt vector table of 8086. So I hope you understand this session, and after this session we are moving into our second unit, which is a very interesting and programming of 8086.